Right. So, look, we have a picture. Brilliant. So I can now dive in. So, yeah, so I'm not going to talk about how you build with a build system, but I'm going to talk about something more visual. So first of all, hi Warszawa, or Dzień dobry, Warszawa. I'm Martin, I'm from Switzerland, Zurich, and I work for a startup called Archeologic. And what we are doing is we're trying to visualize space in an interactive way on the web. And I really love the web because it's an open platform and everyone can build for it. So I'd like to push the borders, and so that's what I'm going to talk about today. So today we're going to learn a bit about how we make 3D happen on the web. So let's go back into the history, because it's quite interesting. So 3D on the web sounds like really new, but actually it isn't. So in 1995, we had VRML. That was a clusterfuck and was really bad, and was a lot of XML, and it was very proprietary, and you had to have specific tools to edit it. So that didn't really fly. Next up, 2001 was X3. That's how you pronounce it, because it's free as in freedom or free beers. And it's still XML, and it's trying to be declarative. And you can basically see here, we're describing a scene that should be sort of immersive, which means that there's no controls overlaid. It's just the plain 3D thing in the browser. We have a scene, which is basically a stage that we put things on. Then we have a shape, which is a box with certain dimensions. And it has an appearance, which is a material with the color that is red in this case. All right, that looks kind of cool, but it was a bit too much overhead. So nobody really used that. It's actually still in our browser. So if you use Firefox or Chrome or Safari or Internet Explorer, you can still render these things, and they are interactive. But nobody uses it because it's really heavy-handed, and you don't really have much control over it because you built these XML files, and then, right? So in 2004, something else happened, which was the canvas specification was used. Who here has been using canvas before? Show hands. Who here hasn't been using canvas before? Show hands. I now know who's checking their emails. All right, so with canvas, we now had access to bring pixel data on screen, which is nice, because beforehand in HTML, we only had images, and we could trick around with one pixel diffs and CSS and JavaScript, but we didn't really have access to the graphics card. And with this, we now have a way to actually put pixels onto the screen really fast, so we could do things like games and stuff. Really cool. But then in 2011, someone thought like, yeah, 2D is nice and fine, but you know, we need a bit more control to actually have performant 3D. Because with 2D, you can actually also do 3D, because all you have to do is basically fake it. But it's not really performance, so we wanted more performance. So in 2011, there was an experimental release of WebGL, and a bunch of browsers supported that and still support it to this day. And we could now have more powerful operations. Actually, that should be do 3D operations. And in 2013, we finally had WebGL 1 stable. And since then, pretty much every browser implements them, including Safari, including iOS, including Microsoft Internet Explorer, everything up from 11, I think. And we have basically a stable foundation. Now we are working on WebGL 2, which brings a bunch of more performance boosts to the web. But what's the difference, right? Because, okay, 2D has GPU access, and WebGL has GPU access. So why is it a big deal? Well, in 2D access, basically what you're doing is you have your JavaScript code talk to the CPU, and the CPU fetches the pixel data from the the video RAM from the, so it transfers data from the GPU, calculates each pixel after the other, and then pushes the data back onto the GPU. And then the GPU puts it on screen. That doesn't sound too bad. But with the WebGL specification, we got much more power. Because here you see 3 colors. So the blue boxes here, or there, that's JavaScript. And we have 2 arrays that we specify. One is the bunch of points, and the point in 3D space is called a vertex. So we have a bunch of points, and the faces basically is an array that tells how these points are connected. So if you ever heard of like, oh, it has this many polygons or this many triangles, that's faces, that's talking about faces. Usually you use triangles because with triangles you can pretty much approximate every single shape that you may want to build. So we have these two arrays and then we push them into the green boxes, and the green boxes are what happens on the GPU. So this entire pipeline, or the majority of the pipeline, happens on the GPU. It's not really on the CPU anymore. And you have the GL buffers, which is basically the GPU version of these two arrays. And we have vertex shaders and fragment shaders. And so what happens is we have these points, and we know how to connect them, but we then sort of need to figure out where in space they really are. Like, this is my camera, it looks at this direction, so I know that this thing is outside of my camera sphere, this one is actually behind me, and if I turn the camera, oh, now I have to render this one because it's actually inside my camera viewport. So that's what the vertex shader does, and does this really, really quickly, because it does it in parallel, and it can do thousands of points, millions of points in a single cycle. So that's much, much more powerful than the CPU, which can do 1 pixel per cycle. All right, so now we know where the points are. So we get what's called a fragment. So that basically says, like, you have to color these pixels on screen later on. And then the fragment shader kicks in. And the fragment shader, again, is a program that runs on the GPU as the vertex shader. And what it does is it goes for each of these texels, or pixels inside the fragments, and colors them accordingly. Like, if you have an image that you want to put onto a triangle or something, that's where it happens. And also, this is parallelized. So this does billions of pixels in one go. Really cool. And how do we write these programs, or can we actually influence these programs? Yes, we can. But it's running on the GPU, and it's highly parallel, so we can't write them in JavaScript. So that's why there's a red box as well that says shader code. Shader code is written in a language called GL slang, or if you would spell it out, it's GLSL, so the GL shader language. It looks a bit like C, but not that complicated, and you don't have pointers and shit, so it's not too bad, don't be intimidated. But you can use these programs and manipulate them. So for instance, you could write a program that, instead of just putting on a color, sort of makes it look like this water and it's reflecting and half translucent and stuff. So you can make it really, really cool effects with GL slang. You can also crack passwords or mine bitcoins. Not that you should do that on your visitor's GPU. Actually, you can't, because WebGL has sort of blacklists and it's going to find patterns if you try. So there's security considerations going in there. And then we get pixels. So let's run the numbers. So if we think of this, actually that's outdated math. But you have a not too large screen. I mean, 720 or 1080 HD is much more pixels than that. So we have 920. Actually, that's not correct. Let's actually update these now. Screw that. No, let's not update these numbers. So we have nearly 1 million pixels. And each pixel is 3 bytes. Actually, it's 4 bytes, really, because you have an alpha channel as well, which says if it's opaque or transparent. So 3 bytes, that's 2,764,800 bytes. And we remember it has to transfer this from the GPU to the CPU, then run for each of these something, and then put it back. So that's a lot of to and from. And if we want to run with 60 frames per second, we have 16 milliseconds per frames approximately. And the problem with that is that the browser also has to do some stuff. So effectively, we get around 10 milliseconds per frame. So now we have to do our operations in 0.0000186 milliseconds per pixel. That's not a lot of time. Now imagine you do complicated math. Oh, that's not going to go well. Now the cool thing is, if you then compare it to the GPU, a modern GPU is somewhere north of, I think it's 100-ish billion pixels per second. 100 billion pixels. So that isn't that much of a problem. And that's really nice. Sorry, millisecond, no, a second. So it's much, much more performant, and that's really cool. So yeah, these numbers might seem surprising, but it's sort of known. I mean, you can do software rendering, and some games still have the possibility to do the software rendering, but you just know it's not going to be really quick. So this gives us a bit of power. And this is how GLSlang looks like. And this is a fragment shader. So this function is being called with a bunch of parameters that are not explicit. They're sort of like globals, if you want to call that. For instance, where we are in the image, where we are in the fragment, and a bunch of things that you can specify. And in this case, all we do is we define the GLFrag color, which is the spot or the variable that GLSlang expects us to deliver when we're done. And we just say, like, OK, this is going to be red 1, green 0, blue 1, which is pink, and alpha 1, that makes it opaque. And this is run for every single pixel in parallel. And that's really, really fast. And we can do really crazy stuff with it. So time for a bit coding. Because you might now wonder, like, how does that look? Well, the best thing is we don't have to worry about most of it. So this is a tool that's online right now and abstracts away the setup code, and it uses a library that's called 3JS. 3JS abstracts away the nasty, gritty details and gives us high-level concepts. For instance, if I want a box, I say I want a new mesh. And a mesh, if we remember the pipeline thing, we basically have to have these faces and vertices. And luckily, 3JS has a bunch of built-in geometries. And I say I want a box geometry, so it gives me faces and vertices for a box. And I just specify how large I want the box to be. Oh, let's make it not too large. Let's go with 50. But now, how will this box look like? Well, as we know, there's this fragment shader that has to somehow color it in. So there's something called a material that specifies all sorts of properties. So I'm going to use that to make it green, for instance. And I'm calling it a mesh basic material. We're going to come to why it's basic in a second. And I'm going to give it a color. And it's going to be green. Now, you could imagine this to be like shooting a movie, and I said that already. You have a stage that you have to add things to, and that's my scene. And now I'm going to put this box onto the scene, and then it's going to be rendered. And there we go. There's a box. Actually, that makes it slightly larger. So 100 was a good default. But that's looking kind of boring, and it's not really 3D, because you can do that with a rectangle. But we can make it slightly more interesting. So for instance, we could see how the faces look like by making it a wireframe box. OK, and we can make it move. So for instance, this is a callback that's being called on every frame. So I can say, I want to change the rotation. Now we have these 3 axes, right? We have the x-axis, we have the y-axis, and we have the z-axis that goes into and out of screen. So if I want to turn it like this, I'm turning around the y-axis. All right, and this is radians, so it's not degrees. 2 pi is 1 full circle, and this runs with approximately 60 frames per second. So I'm going to reduce this a bit so that's not turning too fast. And we have a spinning cube. All right, it's still not very nice and shiny. But what about we actually load something more intricate? I think I actually have the loader already. Do I? Well, let's get a loader. So here we are specifying that we want to load a thing from a file format called obj and another file format called mtl. And an obj file is basically a text file that specifies all the faces and vertices, so our 2 JavaScript arrays. And then the mtl file comes in to basically say, and I want this image to be drawn on this one and this color to be drawn on this one. So you map these 2 things. And now I really hope that I remember the file name. I'll copy that one. So we tell it where the files are, and these are online conveniently. And then we get a callback whenever that's finished with the mesh. And now I can say, so this mesh might be a little too large, so I'm going to make it a little, I'm making it a little smaller. I make it 10% as large as it should be, or as it originally is, and then I'm adding it to the scene. And if the internet is working and I did everything right, I didn't. Sorry? Good spot, thanks. But still, maybe I got the file name wrong, that's why I prepared myself. So, no, that's not right. That's the one that I wanted. So I'm doing the same thing. I think I had a typo in the name of it, but I'm not entirely sure. Yeah, there we go. Oh, it's not very bright. So I'm gonna make the light a bit brighter. Ambient light. And probably, yeah, I'm leaving that smaller. Scene, add L2. Yeah, it's brighter. So there's our spaceship. Sweet. So we can load 3D models and we can make them move. I could also use keyboard events to sort of have a game from this. Or I can do really, really crazy things. For instance, going back to my original example, let's use a box. So I'm making my box again. Yeah. Box geometry, 100, 100, 100. 3 mesh basic material. I leave it white, and if I did everything correctly, I should now see the box again. Okay, so we have a white box, and I can make it turn again. Box rotation y plus equals math pi divided by 100. All right, and now there's crazy things such as, what's it called? I think it's a new 3 webcam texture. And I can specify what sort of image I want to put on this box by saying a map. And I can say text.texture. And then on each frame, I gotta update the texture. And it should be asking me, maybe it's not 3 dot because I might have, yes. So it's now asking me for webcam access. Let's see what we get out of this. And here I am, trapped in the cube. So you can do really weird stuff. And as you can see, this is really fast because these pixels get actually mapped in parallel onto this cube. And it looks really weird to actually see you going with your hand in front of a webcam and then it's, well, whatever. Oh, help me. So yeah, there's a lot of fun stuff that you can do with this. It could as well come from a video source, obviously, because the webcam is nothing else than a video source. So, right. So what crazy stuff can you actually do with this as well? Well, the next thing is, until now, we have more or less been external to what's happening on screen, right? It's like if you go to a gallery, an arts gallery, you look at pictures, but you're not like in the scene that's depicted, you're standing in front of it. The same with photography, the same with computer games. Computer games are a bit better than just static images or TV because you sort of like, you interact with the world, so you feel a bit like you're in this world, but it's still, if you turn around, you're still in your living room or your bedroom or wherever you have your computer. So you're not really in it. So how about we move ourselves into what's happening, right? And this is exactly what it's about. So this is a Samsung Gear VR. I think it's $99 or $199 or something, and you have to have a Samsung smartphone to go with it. But you can see that she's standing on top of a high-rise building, and if you turn around, you then see the respective image. So it's not sitting in front of something, but being in a situation that you're not really in. So that's pretty fancy. And there's brilliant videos of people sitting in a tram and seeing, like having a virtual reality headset on and seeing a roller coaster, and they sit in a tram because obviously it rumbles a bit. Oh my God. So I've never seen anyone being so excited by using public transport. So you don't have to buy a car, just get one of those and then use public transport. Makes it much more convenient, especially if you have weird or noisy or obnoxious people around you. because you don't see them anymore. Anyhow, but virtual reality isn't that new actually. So this is a quick history of virtual reality. And on the left-hand side, we have what's called the Sensorama, and that was from 1962. Now, I'm pretty sure, as this has been around since 1962, everyone has one of these at home, right? No? Why not? So that didn't really take off because it was too large, obviously. The next thing was they thought, well, it's a bit weird to have a clunky thing that you have to sit inside because you want to sort of move around as well, because it's natural to move around if you're somewhere. So let's put it on people's heads. That doesn't look creepy at all, does it? Yeah, so that didn't really take off, but that's the Damocles sword from 1968. So that's also really, really old. And then it was kind of forgotten for a while, and it was only banned to be in academia. But then Sega, in 1995, thought, you know what? Virtual reality. So they brought up this headset, and I think it's one of the most 90s marketing images that I could imagine. And it didn't really take off, and then there was another attempt in 1996 or 1997 from Nintendo with a Virtual Boy. Who here has heard of Virtual Boy before? All right, it was a huge success, I guess, right? They said it's not, or it wasn't a success, it flopped because it was too expensive. And if you sort of fix the numbers a bit, you're gonna come up with a price of $270-ish, and nobody would pay $270 for such a toy thing, right? So yeah, $270, too expensive. Oh wait. Yeah. Oh, yeah, I forgot. Yeah, no, I mean, totally, you would pay $350, I guess. Or you pay $5. Actually, the $5 is a bit of a lie. So the Oculus Rift, I think Facebook invested billions in it now. It's quite cool and quite fun. But what it basically is a motion tracking camera and a phone strapped to your head. So there's a Samsung Note 3 screen in there. So it's basically using phone technology, right? And if you think about your phone in your pocket, in which pocket do I have mine? It has sensors that tell it like how it's oriented and where I'm looking. And it has a pretty good screen. So why can't I use my phone? Well, you can. So Google came up with a cardboard that when I got mine from China, it cost like $2. And you can put your phone in. Obviously, it's not just $2 because you have to have a phone in the first place. That's actually capable of rendering 3D. But it's quite cool, and it actually gives you more or less a comparative or comparable quality and an immersion. So the hardware has changed and now is pretty much accessible to everyone who has a smartphone. That's really nice. And you can do things like this with that. So that's someone using the Oculus to walk through an apartment that does not exist. And it's really, really fancy because we had an architect in our office trying it out with a building that hasn't been built and going, this is not bright enough. I have to actually change something. So he was able to find out a flaw or learn about a flaw before he started building the building. Nice. Another thing is a corporate real estate developer had to sell flats that weren't built in the premium sector and try to convince someone that a flat is going to look like nice, it's going to be a bit hard. So car manufacturers do a trick, for instance, when it comes to cars. You can customize your car because psychologically, when you start customizing a thing and make it your own, you sort of have a binding to it, and you're probably gonna buy it if you can. So the same applies for apartments. So they could walk through their potential future apartment and furnish it and change it, and they could say like, I want my kitchen to be red. No, that looks crap. Green. Yeah, that looks good. That was really successful, and that's really cool stuff. So let's try this out. So this is a modified version of the cardboard, because it's not from cardboard, it's actually capable of traveling with me because it's made from plastic. Slightly more expensive, like $15. And you can do something like this with it. So Yeah. This is not going to be real life coding, but it's probably going to be fine as well. It's the wrong workspace. So it's, whoops, it's code, it's DevFest Live, I think. And no, it's the wrong one. It's DevFest Coding, and it's live. And in here, and I'm going to make the font larger once it's started. Should have been sticking to Vim, it's faster. So in here, we're doing something relatively simple. So you see a little more of the setup code that was hidden in the live coding editor. So here we're loading a couple of modules, and I'm going to use that screen because I can point better at it. So here we are setting up what's called a world, and it's basically the wrapper around the it's a higher level than 3JS, which is higher level than raw WebGL. And I'm going to say the camera shall be at the origin point and run this function on every frame. And here we have, it's called box, but it's actually a sphere. And it has a material that's loading from an image. And then we have two things. We have a VR manager, which gives us a little button. And we have a VR control thing. The controls are bound to the camera and make it turn according to the sensors from the phone. And so all we have is here we are updating the sensor data, so the camera position, and here we are rendering the camera onto the scene. And here we are having what I would call the sky around us. So it's a large sphere. It has a radius of 500 units around us, or 250 in each direction. And it's rendering on the inside. Normally it would only render on the outside, but we're inside this thing, so it's going to be rendering on the inside. And it gets a map, and we've seen that, so I could use my webcam here, but I'm using a texture called Zurich JPEG. All right. And why am I doing this twice? What if? And why am I never adding this to the scene? Should obviously be adding this to the world at some point. Whoops. World, add. Oh, it switched keyboard layout. And if I'm serving this, too many servers running. I'm going to see something like this. So this is Zurich. I highly recommend you visit at some point. And I can use my mouse to move around, or I can use my keyboard. The keyboard is not so nice because I can't just keep pressing, and I can put it into full screen mode. Or what I could also do is, and I'm using another image because I'm not having the same Wi-Fi connection on my phone right now. So I could do Chrome. Oops. How did it switch to British keyboard? It's really confusing. All right. And accept. I'm doing this so that I can actually show to you what's going to happen on my phone. I'm not sure if you knew this already, but you can actually stream the screen content theoretically. Oh no, I can't because Chrome updated and the Chrome here hasn't updated. Congratulations. How does that work? Aha, okay, in Chrome Beta that kind of works. All right, so now I'm going to pick an image. So I was in Paris last week, and I wanted to go up the Eiffel Tower, and boy, that didn't happen because there's a ton of people with the exact same idea, so pre-register if you go there. And now it's loading this image, and I hope that the screencast now works. Yes, it does. And I put in my phone into my headset. Oh, that wasn't very clever because I have to press the WebVR button first. Did that fail? Of course it, no, it didn't. It just, it works on my phone, but it doesn't work on the screencast. Now it comes up. Wow, an amazing performance of 0.2 frames per second or what. So let's re-inspect this and hope that the inspector does not cancel on me. Come on, that usually worked. You can try it out later on if you stop by. But for those who can't see, I'm seeing two different images. Shit. Let's try reloading. Maybe that did the trick. Nota bene, do not update your Chrome before a presentation. It's just not a good idea. Oh, come on, screencasting, don't do this to me. Why would you do? No, the tab is not inactive. You're lying. And now my phone is about to crash. All right, that's brilliant. Thanks, Chrome. Thanks, Obama. It must be someone's fault, and it's definitely not going to be mine. So, the tab should not be inactive, you bugger. Let's try this. Aha. And now this. It's trying some, shit, it actually did that now. So let's hope that it comes back, and I hope that it comes back with a better frame rate than before. Bummer. But the theory is you put it in here, and then you can move around, and you can actually see as if you would be at the spot that you are seeing in virtual reality. And unfortunately, Chrome sabotaged me here. Come on, do that again. You can do it. I have faith in you. Right, okay, it shows one image and only one image. And that's only when it shows down. That's kind of beautiful. Right, so no, that's not it. I'm sorry. Bleeding edge is called bleeding edge because you get cut every now and then. Right, so that leaves us with a bit of outlook into the future. So right now, we are able to do this. And we have a couple of problems. One is a problem known to pilots that have been in flight simulators since, I don't know, 20 years or so, or 30 years. It's motion sickness. Because your brain is actually wired so that it sort of detects if there's a mismatch between what your eye sees and what your ear says, and that can happen. So my experience is 1 in 4 people has this. So we are 16 people in the office, everyone trying an Oculus Rift. 4 people vomited. A bucket full of fun. But researchers found that if you add a fake nose, that goes down by 25% approximately. And it was true, only one person had problems afterwards, and they weren't vomiting, so that's a win, I guess. And it doesn't have to be like your skin color or something, it just happens to have to be sort of here, and it has to be sort of triangular, and then your brain goes, yeah, there's a nose, I'm fine. We also don't know how to design interfaces yet, really, like buttons, text input, not really, because you can't see your hands most of the time, or even if you can, it's kind of weird because you're not really touching something. We don't know how to navigate between things because, as I said, you don't really have a classical UI. Maybe teleporting and portals is a thing. Now you think with portals. And the opportunities are great because you can use this for education. You can take an entire class of kids somewhere where they can't go, like ancient Rome. You can go to Rome, but you only see ruins. But imagine you go to a virtual replication of how the Forum Romanum looked when it was actually in full operation. You can use it for therapy. You don't really want to take someone with anxiety, social anxiety, into a crowd and go like, no, and they may have a breakdown. But you can sort of simulate it, and you can pull off the headset whenever it gets too tense. So that's really cool as well. And obviously entertainment. So Oculus announced that they have Netflix on board, so you can literally, over the internet, meet up with a friend who can't just join you and sit on a couch and watch Netflix. It's a bit weird, but times change, I guess. So that's the opportunities that we have. And there's a few guidelines already for cardboard development that also applies to Oculus, in my opinion. But we're really on the beginning of this. We are still figuring this stuff out. And it's really cool. And if you want to experiment with something, that's where you can go. But don't overdo it. This scene from Jurassic Park made me angry because I'm like, there's a velociraptor, it's gonna eat them. Why is this computer so stupid and has this oh, that looks cool. But I mean, there's a velociraptor, it's gonna eat them, oh my God. So don't overdo it. If you're like, oh, I'm now gonna build all my websites in WebGL and virtual reality, don't. You know when it makes sense? Do it. And it makes sense when you talk about space. So we are 3-dimensional beings, and we live in a space, and if you want to represent space, text and images are so then 3D really makes sense. And now I want to close with a quote from Steve Jobs and modify it. So Steve Jobs at some point is quoted saying, "The computer is the most remarkable tool of our time. It is the equivalent of a bicycle for our minds." And I like to say, VR is the second most remarkable thing that we built so far because it's the equivalent of a teleporter of our minds, or for our minds. And that's really, really cool. So, dziękuję, Falsy values. I hope that was more or less right. Slides are online. Thank you very much for your attendance. You can try out the virtual reality stuff in a bit, and thanks. Whew.
Hello.
Hello.
Okay. Is there any support for bump maps?
Sorry?
Is there any support for bump maps in 3D?
Yes, there is support for bump maps, mip maps, light maps, environment maps. So basically what you have is an entire OpenGL 2.0 ES implementation, so everything that works there works in WebGL, including bump maps. Welcome. I think that's it for the questions. Just come by and talk to me. I'm here for you. Thanks.
Thank you, Martin.